Engine performance problems such as faults in the fuel system or faults in internal engine components may generate the same overall symptoms. To troubleshoot these problems, technicians use knowledge and experience to narrow the list of possible fault causes. To help troubleshoot these faults, this module describes typical mechanical fault symptoms and provides tools and techniques to troubleshoot each fault. Engine performance problems fall into three basic categories: drivability, engine vibration, and oil consumption. Each category includes unique symptoms with specific troubleshooting. Engine mechanical problems can cause a rough idle, low engine power, misfire, or fuel trim problems. Unfortunately, each of these problems also point to a fuel and emission control system fault. Because of this, when technicians see drivability problems, they must decide if they are dealing with a mechanical fault or a fuel and emissions fault. This module provides several checks to help separate drivability problems from engine mechanical problems, but not all faults can be divided using these checks. Technicians who cannot troubleshoot both systems should check over the engine mechanical system, and if they find no mechanical fault, pass the car on to a knowledgeable drivability technician who can correctly evaluate the fuel system. Excessive vibration symptoms can also come from sources outside engine mechanical faults. This module provides techniques to isolate engine vibrations from other vibration sources and includes several troubleshooting steps designed to isolate the vibration source. Unlike drivability and vibration faults, oil consumption problems have a single symptom: oil loss. Any engine with an oil consumption problem has a mechanical fault. These faults include simple oil leaks from seals or gaskets, or an internal fault that allows oil into the combustion chamber. Most engine faults affecting drivability involve problems in the intake manifold or combustion chamber. Faults such as intake manifold leaks, tight or leaking valves, or leaky piston rings can change the air-fuel ratio. These faults may lead to low power complaints or a rough idle. Because these complaints may set a DTC, a car with an engine mechanical problem may arrive at the shop with a malfunction indicator light. Engine mechanical faults do not set DTCs that reference circuit performance or bad electrical readings caused by defective sensors. Only evaluate engine mechanical condition when a DTC references fuel trim or misfire, or mentions an engine mechanical system such as VTC, VTEC, or the intake air system. For VTEC and VTC control systems, the Service Manual DTC troubleshooting procedures should provide you with effective troubleshooting and quickly isolate mechanical faults causing the DTC. Misfire and fuel trim codes requires more troubleshooting. Both codes may relate to a fuel control problem or an internal engine fault. For misfire DTCs, check the scan tool misfire counter to see if the problem applies to all cylinders evenly. If all cylinders have high misfire counts, it is unlikely that an engine fault set the DTC. If the misfire counts point to a specific cylinder, include mechanical problems on your list of possible problems. For fuel trim DTCs, check engine vacuum at idle. The engine should show about 20 inches of mercury at sea level during idle. If the engine does not reach this reading, look for problems such as intake manifold leaks, incorrectly adjusted valves, leaky piston rings, or out-of-time camshafts. In rare cases, the PCM may set a misfire code due to mechanical binding. Since the OBD2 system evaluates misfire based on crankshaft movement, mechanical faults that affect crankshaft rotation will show up as misfire. When a mechanical problem sets a misfire code, The scan tool counter typically shows misfire on several cylinders, while other cylinders show little or no misfire. The scan tool data may also show that the misfire only occurs at a specific RPM or with a particular load on the engine. If you suspect a problem caused by internal binding, remove all spark plugs and rotate the engine by hand. Be sure to rotate the crankshaft at least twice in case the binding is present in the camshaft bearings. If you feel binding during this test, remove the accessory drive belt and test the engine again. If this eliminates the binding, check all accessories for binding. If the binding remains with the accessories disconnected, remove the timing belt or timing chain and check for binding again. If the binding goes away with the camshafts disengaged, check for binding in the camshafts and cam drive system. If binding still remains with the crankshaft disconnected from the camshafts, the problem is most likely in the crankshaft bearings, but also check for binding in the transmission pump or input shaft. We can separate vibration problems into two categories: vibration transfer and internal balance problems. Vibration transfer refers to normal engine vibrations that find a path into the driver's compartment, while internal balance problems refer to excessive engine vibration caused by broken or incorrectly timed components. Balance problems may also occur in the transmission and driveline of the car. For this reason, check for a balance problem with the engine in neutral, radio off, and the car at a standstill. These conditions limit vibration sources to the engine, clutch assembly, or torque converter. Under normal conditions, engine mounts and rubber exhaust pipe hangers isolate engine noise from the driver. When an engine mount collapses or components are misaligned, vibration transfer occurs. With this fault, the repair order complaint may read excessive vibration or excessive noise. Problems caused by vibration transfer are often intermittent. During normal operation, torque moves the engine back and forth on the engine mounts. If a part has insufficient clearance, vibration transfer occurs when the engine rocks and two metal parts make contact. For instance, a vibration problem may only occur under acceleration or during braking. If symptoms point to a vibration transfer issue, visually check for evidence of vibration transfer. Make sure the engine mounts are aligned and check for scuffed paint or polished metal where driveline components could rub against the vehicle body. Engine mounts can create vibration transfer through several faults. In addition to misaligned mounts, many of our vehicles use engine mount control systems. These systems include a vacuum chamber or electronic solenoid inside the engine mounts to isolate engine vibration. A defect in this system sends excessive vibration to the driver's compartment, often at idle. Electronic engine mounts used on VCM engines and some vacuum-controlled mounts include a hydraulic chamber filled with oil or fluid. If the chamber bursts, hydraulic fluid drains out and the mount collapses against internal stops. Vacuum-controlled engine mount control systems use a vacuum chamber to change the mount's dampening ability at idle. If a vehicle with this type of mount arrives with a complaint of excessive vibration at idle, make sure the control system is working correctly. Confirm the PCM commands the solenoid on, check solenoid function, and inspect the vacuum lines for cracks or disconnection. If the engine mounts are out of alignment, a service news article includes a mount neutralization procedure. This procedure places the engine in the correct mounting position, allowing it to move freely without transferring vibrations to the driver's compartment. During a visual check for friction between the engine and vehicle body, pay special attention to the exhaust system. This system bolts directly to the engine and extends down the length of the vehicle, making it the perfect vibration broadcast device. Like vibration transfer, engine balance problems may only appear at certain times. The vibration will relate directly to engine RPM rather than vehicle speed or load. If the vibration always occurs at a specific RPM, you've probably identified an internal balance problem. If you determine the fault is an internal vibration problem, you need to isolate the engine from other possible vibration sources. As we showed you earlier, first check for vibration with the transmission in neutral. If the vibration remains, disconnect the accessory drive belts and retest. Removing the belt eliminates vibrations caused by the accessory drive system. By isolating this system, you won't tear down the engine when the vibration is actually located in an engine accessory. Internal vibration problems are created by broken components, either during engine assembly or after incorrect service procedures. If a vehicle arrives with a new vibration complaint after several years of service, first check its service records. Look for engine work such as a new timing belt or a recent transmission replacement. If the car had recent repairs performed, check the work for loose or misaligned parts before any other troubleshooting. It's time to troubleshoot on the car. Check for loose external components before digging deeper into the engine bay. A loose torque converter or alternator bracket is a valid vibration source. Tightening these loose external components can quickly solve a vibration problem without the hassle and expense of major engine disassembly. Checking for vibration problems, tools such as a mechanic stethoscope or chassis ear may help narrow down the location of a vibration, if the vibration also generates an unusual noise. Engine stethoscopes work just like the doctor's instrument, allowing you to check noises at many points on the engine. Chassis ears use several microphones and an amplifier to accomplish the same result. Both external and internal faults can lead to oil consumption. External faults or oil leaks leave visible evidence of the oil loss. The evidence may be oil residue on the engine and vehicle frame or spots underneath the car. This module covers internal oil consumption faults. In this section, we discuss the internal faults that cause oil consumption. Worn valve guides allow oil into the intake or exhaust system. Worn or sticking cylinder rings pass oil from the crankcase into the combustion chamber. In each case, the oil is burned in the combustion chamber or exhaust system and exits through the exhaust pipe. Some oil consumption is normal, so before attempting a repair, evaluate the symptoms to see if the vehicle needs immediate attention. If the car always blows white smoke out of the tailpipe, the car suffers from excessive oil consumption. However, on most vehicles, oil smoke only appears during certain operating conditions. Identifying when the smoke appears can help troubleshoot oil consumption problems. When a vehicle produces white smoke at all times, the engine may have worn out internal components such as valve guides or piston rings. However, first check for problems such as poor oil quality, excessive oil fill, or a defective PCV system. This training module provides you with these basic checks in the Initial Checks section. A vehicle that produces oil smoke at engine startup has oil dripping onto the intake valve through the valve guides. A small pool of oil accumulates on the intake valve and creates a puff of smoke at startup. As the valve stem seals and valve guides degrade further, they begin allowing oil into the combustion chamber during high vacuum conditions. If these checks find a problem, replace the oil and look again for white smoke with the engine running. Before condemning an engine, check the oil level and condition. On some vehicles, age and time may have thinned the oil, or someone may have overfilled the crankcase. Both these conditions force oil into the combustion chamber, leading to oil smoke. During initial checks, make sure the oil level is correct and the oil is clean with good viscosity. If these checks find a problem, replace the oil and look again for white smoke with the engine running. Also check the PCV systems for faults. If the crankcase is not correctly vented, the PCV system can feed oil into the combustion chamber. To check for this fault, clamp the PCV hose or block the PCV system. With the system blocked, check for smoke while driving. If the oil smoke clears up, check the PCV valve and crankcase venting system. If your initial checks did not identify a problem, evaluate cylinder performance to identify faults. Without excessive smoke may still suffer from excessive oil consumption. When an owner complains about excessive oil consumption on a car without visible smoke, measure oil consumption using the Oil Consumption Job Aid. Using this test establishes exactly how much oil the car is using. The Job Aid also includes a repair flow chart. This concludes the module on engine mechanical performance. Using this information, we hope you can effectively identify mechanical faults and isolate mechanical problems from fuel control system faults.